morning, and I have class Saturday afternoon, but I just have that approximate and early to
Well, good afternoon. Welcome back to Chemistry 401. A couple announcements. One is next Wednesday is your first exam, and we'll cover chapters 14 and 15. Chapter 14 is, of course, kinetics. Chapter 15 is, of course, equilibrium constants. And as you'll see, and as you have seen, for chapter 16 and 17, we continue with equilibrium constants. Your information. Logan, if you could go ahead and sit down. Yeah. What do we have here? Where was I? So equilibrium constants as it applies to the homework that you just turned in, homework number 2. So homeworks 1 and 2 are inclusive. I've already been asked to place the key for homework 2 online. I will try and do that later today. If you don't see it as early as tomorrow morning, please remind me, but I'll plan on doing that. Let's see. Yes, and here we are. We're in the middle of chapter 16. We have some more time. What I'd like to do, and this is relatively unheard of, I would like to spend some time, on Monday, reviewing some concepts for the exam on Wednesday in lecture. Crazy, but we are far enough ahead that I'm going to do that. And so we will reserve probably 30 minutes, plus or minus, to be determined for questions, or actually I'll plan on bringing some material that I think will be important for you to know for Wednesday's exam, and hopefully that will be helpful. Another announcement, so I came up with some companion problems for chapter 16, not even on exam 1, but for second exam, you will have some companion problems to work. I came up with a practice exam. This practice exam in particular has a last question on the exam, which is on par with the types of last questions you should expect to see, the one last question you should expect to see on your exam. And what I will say about this practice exam is that it is not as fine-tuned as your exam will be. Your exam will be very fine-tuned, meaning the questions will all be hopefully clear, and I'll work hard to make that happen. Although you can always ask questions during the exam. Worst case scenario, I say, I'm sorry I can't answer that. That's part of what I'm testing. And then homework number 3 is also up here. Homework number 3, we have at least 2 Wednesdays until that is due. But we should be finished with chapter 16 as possibly as soon as today, actually, and definitely by Monday. So you will have plenty to do. Any questions before we begin? All right. Well, let me get my lecture materials up there. And let me find out where we left off. We left off in chapter 16 on page number 13. So we still have a little ways to go. Good. Now, as far as lecture material, we're on chapter 16. Chapter 16 is acids and bases and acid-base equilibria. Now that you've completed chapter 2 homework, chapter 15 homework number 2, you might have seen some problems that look sort of familiar to what we're doing right now. There we go. Yeah, thanks. There, thank you. All right. So we did acids, and what we found for acids is that acids had Ka values for what are called the acid dissociation reactions. Acid dissociation reactions always look like this: acid plus water goes to hydronium plus conjugate base of the acid that you started with. Now we're going to jump in and do bases, base strength, and Kb. At their heart, these are all capital Ks. These are all equilibrium constants, which means they're always products over coefficients. What's nice about this chapter is all the coefficients are ones, so we don't have to worry too much about that. Let's start with an example for ammonia and write out the Kb reaction and its Kb value, although its Kb value is displayed on the next slide. Now we're going to write base. Kb reactions are base dissociation reactions. That will be base plus water. In this case, water is the acid. For a proton donor, donating a proton to ammonia, are products. Well, if water loses an H+, that will leave us with the hydroxide ion. If ammonia gains an H+, it becomes the ammonium ion. And similar to some of the things we did with Ka reactions in our last lecture, the ions that you see on this far side should look familiar to you in general. Kb in this case is going to be 1.76 times 10 to the minus fifth. We can also write out the equilibrium constant expression, Kb. It's going to be products over reactants. And if you remember what I said is that we can we can treat anything as an acid previously. If it's an acid, then it donates a proton to something else. We can do anything, treat anything as a base. Well, hydroxide will be a base. Put it in water. Bases get protons. And in this particular example, we end up with the same things that we started with. And Kb is just 1. We know it's 1 because the concentration over concentration will by definition be 1. We have some Kb values over here. Not much more to say about that other than the Ka and the Kb values are on your conversion and equation sheets. Hopefully you've been using your conversion and equation sheets to do your homework, to do your discussions, to do your companion problems, because you will have the conversion and equation sheets with helpful numbers on it and equations as part of your exam packet. So you will have those. So anything that's on there you don't have to memorize. For example, you don't have to memorize Kb values because they will be given on your exam. Same thing with Ka values. And of course, at this point, we're talking about your second exam. Before you flip, and I apologize for this, I didn't get to do, there we go, acid and base properties of the products. If we were to look at this reaction going in the reverse direction, the ammonium ion would be donating a proton to hydroxide. Ammonium is an acid. Hydroxide is, of course, a base. We've known it as a base since Chem 400, if not Chem 300 or earlier. We've made assignments right there. Any questions about this? Where we're going, by the way, is we're going to start talking just about the acid properties of the ions themselves. I have a question for you then. Based on this Kb value, what kind of base is ammonia? Strong, weak, or inert? Do you remember? It is a weak base. We said it was a weak base in Chemistry 400, or at least I did, and Kb values for weak bases will be between Kb values of 10 to the minus 14 and 1. This is the range for weak bases. And there's the same range for weak acids as well. Any questions about that? No. Now let's talk about the acid and base properties of salts. To start with, we'll talk about the relationship between Ka and Kb for a conjugate pair. The conjugate pair we're going to choose is going to be acetic acid and acetate ion. Those are a conjugate pair because they're only different by a single H+. And the question we're going to ask is, what is the Kb value for acetate? What is the Kb value for acetate? CH3CO. And to do it, we're going to start by writing out a Ka reaction. For acetic acid, Ka reaction is going to be acetic acid plus water. Then we're going to write out a Kb reaction for acetate. And these reactions will look very similar. We'll see. So all I've done is I've written a Ka and a Kb reaction. They are specifically for a conjugate pair of acid and base. We know the Ka value, at least we can look it up. It is 1.8 times 10 to the minus 5th. We're looking for the Kb value. But what we know, and this is definitely something that could be on your exam, is that if you add reactions, you multiply K values. For example, and let's see here, before I write down what's left here for our third reaction down here, I can show you that there's acetic acid on the reactant side, and there's acetic acid on the product side. Acetate as well. and then write what's left. What's left is 2 H2Os. There's my double arrow, goes to hydronium plus hydroxide. This is our Chemistry 401 version of Kw. Which is 1.0 times 10 to the minus 14. And what I've said is, if we know, so when we add reactions, we multiply K values. And since we know Ka and Kw, we can solve for Kb. And I'll put in the fact that this is the Kb value for acetate, so that when you reflect on these notes later, you'll see exactly sort of what we're doing. And I will point out to you that we are talking about the Ka and Kb for a conjugate pair. These are a conjugate pair. And I get that the Kb value for acetate is 5.6 times 10 to the minus 10. And I know I've written a little big here. I do have more to say about conjugate pairs coming up. So, oh, it's a thing of beauty, isn't it? Look at that. Well, except for the fact that none of these numbers have any units. But we're still working on that. Anyway, but this is all stuff that we've done before. Add reactions, multiply K values. Now we know the K value. And this is always true, meaning that Ka times Kb for a conjugate pair equals Kw. So let's for a conjugate pair, Ka times Kb equals Kw. It's okay if I erase some of this stuff so I can have some more things to say over here. I'll start by erasing some of the stuff. What this means, well, let me ask you this question first. Acetic acid, strong, weak, or inert acid? Based on the Ka value right here. It's a weak acid. We knew it was a weak acid last semester. Now we have a number to it. Acetate, strong, weak, or inert base. Well, I erased it. I had it up here. So if Kb is between 10 to the minus 14 and the number 1, it is weak as well. Also weak. Next point is, weak acids have conjugate weak bases. Wa for weak acid. Weak acid, I guess it's plural, I'll write a little s in there. Weak acids have conjugate weak bases. And I stated that last lecture, and now we have the Ka and the Kb values to back it up, and the method of proving What you're seeing, though, is if Ka and Kb values fall between 10 to the minus 14 and 1, that is a very wide range. There are lots of weak acids. I think we said last semester, and this still holds, there are 7 strong acids. There are thousands of weak acids. There are thousands of weak bases. True. Next thing I want to say is that even though the weak acid and the conjugate weak base, they're both weak, the stronger the weak acid, the weaker is the conjugate weak base. Let me show you an example, and then I'll write something like that. See how the acid's 10 to the minus 5th? The base is 10 to the minus 10. The bigger this number becomes, the smaller this number becomes. So maybe this is what I want to say. Stronger weak acids. I don't even know if this is. Does it make any sense? Stronger weak acids have weaker conjugate weak bases. Let's just go with this. The stronger the acid, the weaker its conjugate base. Let's go with that. Would that work with strong bases? Yes. If the base is strong, that means its Kb value is greater than 1. Its conjugate then, by this relationship, must have, its conjugate acid must have a value less than 10 to the minus 14. And that is the definition of inert. Inert acids, inert bases, means they do not change the pH of the solution. Does that answer your question, Angel? Yes. It is true for all acids and bases. That's why I'm going to state it in terms of that. So the stronger the acid, the weaker is its conjugate base. The stronger the acid, the weaker is its conjugate base. I think what's confusing to me, and some may be confusing to you, is that both the weak acid and its conjugate weak base, they're both weak. So strong base goes with inert acid. Strong acid goes with inert base. But weak goes with weak. Any other questions about that? It is because of this relationship, and I should box that. We use this a lot, as you'll see. That's what I wanted to say for more about conjugate pairs. Now I'll ask the question, what is the pH of a 0.11 molar solution of sodium acetate? Oh, there shouldn't be a minus on it. And here's what I suggest, and we started doing this actually as I talked to some people for homework number 2. Sodium acetate is a salt, an ionic compound that dissolves in water. When it dissolves, it breaks into sodium ions and acetate ions. And what I will tell you is that sodium ion, everything, so first off, solubility rules, everything that has a sodium ion attached to it will dissolve. Second off, sodium ion is an inert acid. And as I come over to the periodic table over here, I will tell you that all of the group 1 and group 2 cations are inert acids. All group 1 and group 2 cations are inert acids. And at this point, you can choose a certain level of acceptance about that and just memorize it. Or you can also associate the group 1 and group 2 cations with the fact that they're pretty much always spectator ions and other things. They have very few cases where they react. Are you willing to accept it? Okay. Well, then let's focus on these anions. We just did the Kb value for acetate. Yeah. So there's the Kb value. Any value of Kb or Ka, Kb in this case, that is greater than 10 to the minus 14 will affect the pH. So this is a weak base, yes. It will affect pH. That's what weak acids and bases do. Right. If we have a weak base in solution, set up a Kb reaction ice table, solve for the concentration of the products. Yes?
Where are you getting your Kb from?
Where am I getting my Kb from? So we did this a couple slides ago using the relationship that Ka, times Kb always equals Kw. We'll do more of them too, where I'll actually do it explicitly as part of the problem, but we just did that. Yeah. So we have a base. We set up a Kb ice table. What does that mean? Write the Kb reaction. Kb reactions have the base plus water. Let's see, transfer my proton. Aqueous as well. Write my Kb value. All the values in this ice table will be molarities, ICE. I know my initial concentration. My products have 0 or essentially 0. Set up my ice table. And we dream of such easy ice tables now. After the ice tables we've seen on homework number 2, we're like, wow, I can ignore X. Assume X is close to 0 or insignificant compared to the 0.1. X squared equals 5.6 times 10 to the minus 10 times 0.1. We solve for X. 2.4 times 10 to the minus 5th. That is our concentration of hydroxide ion, from which we can find POH. In this case, the pOH is 4.63. And I'm out of space here. I think you have some more space, but I'm going to put the next part up here. pH plus pOH equals what number? 14. Subtract this number from 14, you get 9.37. Which is basic, which is pretty basic, all things considered, for as tiny as this KB value was. Any questions about this process? Where we're going is, you're going to be given a multitude of things and asked what the pH is, including salts now. Yes?
So, like in previous ice tables where we would take our X that we found that was the concentration of the hydroxide, we're not plugging it back in for X to find the specific. We're not worried about the other ones, we're just worried about
good question. Are we worried about this and this? The short answer is, we were just asked about pH. And in general now, and so you still have your first exam coming up, you still care about the concentrations and the partial pressures of everything. And then we'll focus on the pHs, okay? So, yeah, no, and this, I've told a number of people this already. I strongly encourage on the exam next Wednesday that when you solve the problem, or when you think you've solved the problem, that you reflect back on the question and make sure you've answered it. Because this is a case where all I'm asking for is pH. Okay. But on your exam, it will more than likely say, first exam, it'll say, solve for the concentration of all species. Okay. And all is kind of a vague term, so I'll probably list what I want.
Okay. Yeah. That could include like solids.
Could it, so you're talking about exam 1, right?
Yeah, well, because like that one, the one problem is in the homework that had the solid carbon, or it was some molecule that was solid. And I think it was worded like that.
Yes, so on homework number 2, there was a question about how much of the ammonium chloride was left. Is that, anyway, yeah, so there are some stoichiometry questions that are possible on exam 1 like that. But those, and I think what's nice about homework 2 is that we saw the full breadth of possibilities for solids. They never show up in K expressions, whether they're KPs or KCs, and yet they can be a limiting reactant. And sometimes it doesn't matter whether there's 1 gram or 60 or even 120 grams, it doesn't shift the position of equilibrium. Yeah. Anyway, so yes, always read the question. This one just says pH, so that's all the farther we got. Okay. Okay, so classifying salts as acidic, basic, or neutral. Let's do some examples here. The first example we're going to do is sodium chloride. We just said that sodium ion, well, first off, so, and this is my process. You don't have to do this. But my process is break it up into ions, then think about each of the ions. Sodium ion, we just said what the answer was for sodium. Sodium ion, inert acid. Do you still believe me? Yeah, okay, fine. Well, I can't help myself. I'm going to explain anyway. Because I think it's interesting and it's useful to think about. And when I say useful to think about, you know what I really mean? I mean useful to think about because this will come back to help you in organic chemistry, which is life. Anyway, so if that's an acid, what's our definition of an acid according to Bronsted-Lowry theory? donates a proton. Proton is an H+. Do you see an H+ there? Nothing on my sleeve? No, there's no H+ right there. But let's take one away anyway. How many H+ do we have now? We have -1. You know what that looks like? H-. Do you know what the name of that is? Magic.
I like magic.
That is the hydride ion. All of us carry hydride ions in their solid form around on our bodies in the form of lithium hydride batteries. So those are in cell phones. Anyway, so we have an association with these at least. Here's the next question. Knowing nothing other than that we should call hydride ions magic, is that a strong, weak, or inert base? Well, you know its conjugate, sodium ion, is inert. So what's the relationship between conjugate pairs? If you're an inert, your conjugate is strong. Hydride is a strong base. Very strong, in fact. In fact, very strong. And so when you get to organic chemistry and you run into the hydrogen ion, strong base. Any questions about that? All right, chloride ion. And so positive things will be acids. That's your first thought, is acid. Negative things, chloride ion, bases. Bases, well, if that's a base, what's its conjugate? What's its conjugate acid? Bases, by definition, gain a proton. This one becomes HCl. What kind of acid is hydrochloric acid? Strong. What kind of base is chloride ion? Inert. Strong goes with inert. Weak goes with weak, that's what we'll see. Strong goes with inert. Sodium chloride contains an inert acid. It contains an inert base. It is a neutral salt. Meaning that if you take pure water, pH 7, and you add salt to it, sodium chloride, I mean table salt, pH is still 7. Because sodium chloride does nothing to affect the pH of the solution. Any questions about that? All right. Next example. So that was example 1. Let's see, got a couple of possibilities down here. Well, we already did this one, right? Let's do ammonium nitrate. And here's where, so there's no nomenclature test in Chemistry 401, but here's where knowing your nomenclature, knowing how to break these into ions will help. We know this is ammonium and nitrate. Now we will look at their conjugate pairs. Acid, because it's positively charged, that's our first thought. Conjugate base is going to be ammonia. we know that ammonia is a weak base. Now we can look up its Kb value. If ammonia is a weak base, what kind of acid is ammonium? Ammonium is a weak acid. Nitrate ion is a base, conjugate acid. Nitric acid, strong, weak, or inert acid. Strong acid, yes. One of our 7 strong ones, still going to help you remember them. Oh, side note. There are no strong acids on your Ka table. So if you don't see an acid, I mean, your first line of defense is memorize your strong acids. Your second line of defense is if you see an acid and it's not on your list, and you think it's strong, look for it. If it's an acid you've seen before and it's not on your list, it's strong. Nitrate is an inert base. Ammonium nitrate with a weak acid and inert base will be an acidic salt. And when you calculate the pH of an ammonium nitrate solution, you should find it less than 7. A third example. Iron 3 nitrate. Well, the nitrate we've already done. Still, nitrate is an inert base. Now let's talk about iron 3. Is iron 3 in group 1 or 2 on the periodic table? No, it is not. It is a transition metal. We have no rules about them yet. We just have a rule about 1 and 2. Turns out iron 3 does have a Ka value. You can look it up on your conversion equation sheet. When you do, you will see the following. Ka for that is not the right way to do parentheses. There we go. Ka for iron with 6 waters attached is 6.3 times 10 to the minus 3. That's a 3 there, 10 to the minus 3 if you will. We'll talk more about this, but the transition metals, some of them can be acidic cations. Do you have any more room on your page? The next page is blank? Oh, yes. Well, I have more to say about that, but I'm not finished here. Well, yeah, let's keep going. More about classifying. Oh, good. Thank you, by the way. Could you write a Ka reaction for this? Yes. Well, maybe you can, and maybe you can't. I would guess that you can, because all Ka reactions start like this. Whatever I tell you is an acid, plunk it in water. That means water is the other reactant. have it give up a proton, an H+. I see a bunch of them right here. And admittedly, you may not know how to write what's left over. And it doesn't matter that much. But here we go. We took the 6th water, we turned it into a hydroxide more or less, put it out there. The whole thing's got a negative charge. Who knows what that even means? But it's a Ka reaction. Anyway, so we'll talk more about this. But there, some of the transition metals look for Ka values. If it's a transition metal. And we're used to things being weird in the transition metal area. Remember multiple oxidation states when we were doing nomenclature? Plus Fe plus 2, Fe plus 3, etc. All right. So we have even more to say about classifying salts as acidic, basic, or neutral. In this one, we're going to find the Ka value for the ammonium ion. It is related to the Kb value for its conjugate, Kb for NH3, and why we need to do this is that the Ka value for any ions, not on your conversion equation sheet. Kb value for ammonia is on conversion sheet. When we look it up, we have Kw 1.0 times 10 to the minus 14 over the Kb value for ammonia. And at 2 sig figs, we get 5.6 times 10 to the minus 10. You can do the same thing for Kb for acetate. In fact, if you look in your notes, we've already done it. It's the same number. Coincidence? Yes, it is a coincidence. But it does allow us to ask an interesting question, interesting to me, that question being, what if you have a solution of ammonium acetate? We know, as stated right here, that the Ka value is 5.6 times 10 to the minus 10. The Kb value is the same. You can think of Ka and Kb values as Ka is ammonium is trying to give up a proton. Acetate is trying to take a proton. And if they are the same, then they cancel each other out. pH is 7. Because the Ka for the weak acid equals the Ka of the weak base. Anyway, side note, useful to think about sometimes, not the heart of the issue. Any questions? And we just did the example where they're the same. Now let's do an example where we can actually calculate pH. The question is, what is the pH of a 0.157 molar solution of ammonium hypochlorite? And the way we deal with this is similar to things that we've said before. So we have a weak acid, we have a weak base. Always start, well, let's say this, Ka. (5.6 times 10 to the minus 10). If you try and find Kb, you will find that its Kb value is 3.4 times 10 to the minus 7. What's the difference? How many fact powers of 10 are these two different? Approximately. 10 times, 100 times, 1,000 times, 10,000 times? Just looking at the exponents. How much bigger is this number? It's about 1,000 times bigger. Equilibrium constants mean how much reaction occurs, how much of the products. That means this reaction occurs, well, maybe it doesn't occur 1,000 times more, but certainly it occurs significantly more. So, equilibrium constant, approximately 1,000 times greater. Colon, set up an ice. So we've talked about this before. You always deal with the equilibrium constant that is the largest value first. We're going to do the same thing here, even though one of them's a Kb and one of them's a Ka. Set up an ice table. For this reaction first. And this is a general principle that even goes all the way back to your exam in the chapter 15 material. If you have multiple K values, always go for the largest one first. You may or may not have to do subsequent ice tables. It depends. What that looks like is we have a Kb value for the hypochlorite ion, add water to it. An obscenely long ice table. Here we go. We end up with hydroxide ion and hypochlorous acid, HClO. We'll squeeze it in there. We know that 0.157 molar ammonium hypochlorite dissociates into 0.157 molar ammonium, 0.157 molar hypochlorite ion. Now we know our initial concentration here. So many of these, so it's almost as if we're lulling you to sleep, by the way, with these ice tables that all look the same. And then we go crazy next chapter again. But for now, we'll take it. KB. Of 3.4 times 10 to the minus 7. Same ice table we've been doing multiple times this chapter. Ignore x. And this question came up a couple times. I want to say this in preparation for your exam next Wednesday. You'll notice that we can always ignore x when it's added or subtracted to a number that's much bigger. We're never ignoring these x's in the numerator. These x's in the numerator are multiplied times things. So if they're small, it is important. We're only ignoring x when it's added or subtracted from a much bigger number. And then we can always check and see if ignoring x is a good thing to do or not. And with a value of k that is 10 to the minus 7, pretty much you can rest assured. X, which is the concentration of hydroxide, is 7.3 times 10 to the minus 4. From that, we can get POH of 3.14. And pH of 10.86. Question, Kate? And then you square root it.
So when I did my calculator, I did like 0.00023. And then the previous problem we did, I did it and I didn't get that one either. So I was like, I don't know, it's lost.
Anybody else do it?
Yeah, we tried different answers for that. And I was just like, I'll wait.
Well, I don't know. I will tell you, having a solar calculator in a dark room is a bit of a problem. There we go. And being blind. Did you get 2.3 times 10 to the minus 4?
Yeah.
I apologize. I don't know what I did, but I can fix this one. So 2.3 times 10 to the minus 4. Well, let me fix the whole thing then. Oh, that one's right. My pOH is 3.64, and my pH. Thank you for that. 10.36. And I don't know what happened. What's that? Oh.
Everybody needs
Everybody has a
My goal is to get an A with you, so that's still a 90%. Anyway, thank you for that. Any other questions or comments or corrections? All right, then we'll keep going. Question?
For the NH4
You do not have to account for the NH4 because it is sufficiently weaker that as it's trying to make hydroniums, well, let's say this. The hydroxides will basically counter any hydroniums. I was trying to think. I don't. If it's in it, so I'm going to think about how to solve it though. I like to solve things, and let me see if I can reason through this. So we have this. The next biggest K is in Ka. Ka is going to make the pH less than 7. I know I've run into a contradiction. I'll have to think about how to mathematically prove that. I have some ideas. So the short answer is no, you don't do it. The long answer is to be determined. Yes. Okay. Sorry, I can't. I won't say anything else. At risk of going off on a 20-minute tangent that may or may not work. Now I have some ideas. I want to put them down first. All right. Now let's talk about polyprotic acids. A good example is sulfurous acid. If you look on your conversion equation sheet, it has what's called a Ka1 and a Ka2. The Ka1 reaction is going to be for removal of the first proton. Take a proton or an H plus away from sulfurous acid. We are left with the hydrogen sulfurite or sulfide ion. We can look in our table. We will see that the Ka value is 1.6 times 10 to the minus 2. We can use the or we can find the Kb value for the conjugate base. By looking at the Kw divided by the Ka. And you get 6.3 times 10 to the minus 13. This is a conjugate pair. Conjugate pairs Ka times Kb equals 10 to the minus 14. We can also write a Ka2 reaction. Ka2 is for removal of the second proton. And one of the things I'll point out is we will only be doing one proton at a time. One thing at a time is a key part of Chemistry 401. Take the hydrogen sulfide ion, write a Ka reaction for it. And what you can see is the Ka2 value will be given in your conversion equation sheet. It is for the hydrogen sulfide ion, 6.4 times 10 to the minus 8. It will always be much harder to remove a second proton than to remove a first proton. You can imagine that removing the first proton creates this negative ion. If you have something negative and you're trying to take something positive away from it, from a physics standpoint, that is a much harder thing to do. That's reflected in the fact that the Ka2 value is, at least for this one, 1 million times lower. I think we're just going to call this Kb. I don't think there's any reason to call it Kb2. It's just a general Kb. But it is for the conjugate base. And Kb, 1.6 times 10 to the minus 7. On this page, we have hydrogen sulfide being a base. We have hydrogen sulfide being an acid. What's the term for that? The term we've used before, if something can be both an acid and a base, is amphoteric. So hydrogen sulfide is amphoteric, can act as an acid or a base. I think we're going to stop there. We're going to stop a few minutes early, say a couple more words about the exam. So, did everybody get a copy of the practice exam? If you did not, come up and get one. Has anybody looked through this practice exam yet? Let's do it together. I'll tell you what I see anyway. Come on up, pick up a copy. While people are picking these up, I'll just say a few words about my exams in general. Yes, it will be 150 points. If you've read the syllabus, you know that any one midterm exam can have the final exam percentage replace it if that helps you. And so the first thing to say is that no single exam in this class, except the final, is catastrophic. So if you have a bad day, so as much as possible, or a bad week or a bad couple weeks, it's not catastrophic. However, you've done homework 1 and 2. You know what's going to be on that exam or what's covered on that exam. And now you know what you're up against. Then you can see that there's about 2 pages of multiple choice. I would say that I found a couple more kinetics questions than I did equilibrium questions. You can expect it to be roughly 50-50 multiple choice questions and about somewhere between a page and 2 pages. Then in the short answer, you can see number 1, calculate the average rate of reaction. You do have to read that graph. That is not a surprise at all to me. Hopefully it is not a surprise at all to you. You should expect to be able or you should expect to read a graph or something similar. Question number 2, blah, 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 integrated rate law. You should expect an integrated rate law problem, or there's a high probability anyway. Let's see. As I look over this, the only thing I'll say is it does appear a little long, meaning that, again, I didn't, usually when I write your exam, I time it so that you should have plenty of time, or certainly enough time to do it. Number 7 on, well, there are no page numbers, but it's got little dots around it. You have to draw me a picture. I don't know if that'll be there, but certainly a possibility. Anyway. And then the last problem on the exam. I'm always very proud of these. What's the first thing you notice about those plots? The R-squared values? Do any of those lines fit that data?
No.
Interesting. Do the lines usually fit data? When I draw you a graph or when you draw a graph? Okay. So what did you just say, Dylan?
Maybe we could make a third order graph.
Maybe we could make a third order graph. Interesting idea. Let's read the first line of the problem. For the reaction A goes to B, the initial concentration of A is 3.32 molarity, and the reaction is either 0, first, or second order. I anticipated the third order. It is not the answer. That part is what I hope to do for your first exam, meaning anticipate even the wrong directions you can go and answer those questions when I write the exam. We'll see. That's the goal. And I will tell you this, answering this question does have something to do with the fact that those lines do not fit those curves. Other than that, once you figure out that last problem, you will see it is everything you have done before. You may not know how to start, but you will see. And anyway, we can talk about that in more detail next time. Oh, what does B say? Can somebody read B? Jessica, would you read B?
What is the value of the equilibrium constant?
What is the value of the equilibrium constant? What kind of plots are these? Those are kinetics plots. So intriguing. Anyway, sorry, Jessica. Would you finish?
And the value of the rate constant for the reaction B to A.
And the value of the rate constant for the reaction B goes to A. Have we talked about how the equilibrium constant is related to the rate of the forward, the rate constant in the forward and the rate constant of the reverse reaction? It's all in there, folks. And it's meant to be difficult. The rest of the exam, as you read it over, is meant to be straightforward.
That's what you mean straightforward is? What's straightforward?
The last problem is not at all straightforward. And I'm trying to explain to you at least a couple ways where you know something about that problem, even if it doesn't look like it. Anyway, that's all I want to cover for today.